This is the second day of linear programming notes. Two questions for us today. A publisher ships somewhere between 300 and 450 books each week to a national chain of bookstores. Some are shipped from the east and some are shipped from the west. At least one third must be shipped from each warehouse. 37 cents per book from the east and 55 cents per book from the west. Find the weekly order which minimizes the costs. First thing we want to do is determine what our variables are. So we want to minimize costs, and costs are given in terms of number of books from uh, each coast, basically. So we're going to determine the number of books shipped from the east and the number of books shipped from the west, and then that will help us find our objective function. So the cost function, which is 0.37 east E plus 0.55 W. Again, I could use X and Y or whatever. I just decided to use uh, different variables this time just to give us a little bit more practice with that. So now after that, our job is to figure out what our constraints are. And so if we take a look at this and we want to figure out the constraints, um, in order to figure out the constraints, let's take a look at what um, each of our problems sentences have to do with us here. Um, so what we know is that there are between 300 and 450 total books shipped each week. And so since E and W are our variables, E plus W must be greater than or equal to 300, and E plus W must be less than or equal to 450. We know that for sure. But now this other thing is a little bit more confusing. At least one third of them must be shipped from each warehouse. And so if we know that, we have to take into account what does it mean for one third of them to be shipped from each warehouse. So let's just think about it from a logical perspective. Let's say we ship 300 books. One third of 300 is 100. And then the other coast would get 200 of them. Let's say we shipped the maximum amount of books, 450. One third of 450 is 150, and then the other coast would get 300 of them. So what we're looking at here is a relationship of 2 to 1. Basically, if one of the coasts ships a certain number, the maximum the other coast could ship is twice as much. So as we take a look um, at these equations, our constraints are E plus W is greater than or equal to 300, E plus W is less than or equal to 450. And then these two equation inequalities are basically dealing with the fact that W, if E is the smaller amount, then I can multiply that by 2 and get W. If E is the bigger amount, then the um, then I have to ship at least 1/2 of that from W. So W must be greater than or equal to 1/2 E. W must be less than or equal to 2E. And the reason I put W over here is because I'm doing this as W is kind of like our Y variable. So I wanted to write them in an easier format for us to see with slope-intercept form. So if I graph these inequalities, what I have here is, let's make E and W. So I'll go up by 50s. Actually, I can go up by 25s. So each 2 lines will be 50. And likewise down here. So 50, 100, 200, 300, 400, and 450. So the two easy lines to draw are E plus W equals 300. It'd be an easy line to draw if I was good at drawing. So E plus W equals 300, and E plus W equals 450. Now, these other ones deal with some kind of slope situation. Oh, I forgot to get out of my line thing. So I have W is less than or equal to 2E. So that means I need a slope of 2, 2, 2, 2, 2, 2, 2, 2, and that's good enough. Then I also need a slope of 1/2. 1/2, 1/2, 1/2, 1/2, 1/2, 1/2, and 1/2, and that's good enough. So I end up with 4 intersection points: 200, 100, 100, 200, 150, 300, and 300, 150. All of these seem to make sense. If I'm doing a guess, since I'm minimizing something, I'm probably going to want one of these 2 points. And since the east gives me a smaller cost, my best guess would be the point 200, 100. But let's double check that by substituting values in. So as I substitute values in, oh yeah, I forgot that if at least 1/3 are shipped from each warehouse, at most 2/3 are shipped from the other. Oh no, don't move. Please don't do that. And that was something that I kind of talked about with this up here. So we have what happens when we plug things into our cost function. Notice that $129 is the smallest, and I end up with the minimum shipping cost being $129 with 200 books from the east and 100 books from the west. I forgot to shade the region in problem 1. So the shaded region was here, and you could have figured that out by substituting some values in and figuring out where the inequality signs were. Mark, who is ill, takes vitamin pills. Each day he must have 16 units of vitamin A, 5 units of B, and 20 units of vitamin C. He can choose pill 1, which contains 8 units of vitamin A, 1 unit of vitamin B, and 2 units of vitamin C, and pill 2, which contains 2 units of vitamin A, 1 unit of vitamin B, and 7 units of vitamin C. Pill 1 costs 15 cents each, and pill 2 costs 30 cents each. How much of each pill should he take each day to minimize this cost, and what is the cost? Wow. So there's lots of stuff going on. It's very tempting to try and do a lot of different things as variables here because we have vitamin A, vitamin B, vitamin C, pill 1, pill 2. So what we have to do is we have to look at what the actual question is. And since the question that we're asking or being asked is how many of each pill should he take, then that kind of makes figuring out what the variables are a little bit easier. So our variables have to be the pills, not the vitamins. So X and Y are going to be the numbers of each pill. So the question can often help you determine what the variables are. Then our objective function is going to be minimizing cost. So since we're minimizing cost, we're going to take the 15 cents for pill 1 and the 30 cents for pill 2 and take that into account for the cost. Now, the constraints. If we look at the constraints, we are given information about how much he must have each day in terms of the number of vitamin or the vitamin units, so A, B, and C. So those are going to be our constraints. Our constraints are going to deal with vitamin A, vitamin B, and vitamin C. So since those are our constraint variables, or those are the equations or inequalities that I'm going to be dealing with constraints, that may actually help me out a little bit. Now, if I notice, um, pill 1 contains 8 units of vitamin A and 2 units of vitamin B. Pill 1 can, I'm sorry, pill 1 takes 8 units of vitamin A and pill 2 takes 2 units of vitamin A. So if I'm thinking about vitamin A, pill 1 has 8 units, pill 2 has 2 units. So if I'm looking at vitamin A, what I'm kind of thinking is if I have 8 units in pill 1 and 2 units in pill 2, and I add them together, I cannot have that be less than 16. So this must be greater than or equal to 16. And that's kind of the logic that I'm going to use in developing each of my constraints. So if I look at the constraints that I have, vitamin A is constrained in such. Vitamin B is constrained because each unit or each one has 1 unit. And so therefore, X plus Y must be greater than or equal to 5 for the vitamin B stuff. And then 2X plus 7Y must be greater than or equal to 20 for the vitamin C stuff. So if I align my constraints with the equations, that may help us and guide us in what we're doing. So now that I'm doing that, now I'm going to finish by graphing the problem and then substituting values in. So if I, well, first of all, I probably want to label things. So I'm going to label this as X for pill 1 and Y for pill 2. I'll go up by ones. Actually, I'm going to skip lines just to space my graph out and make it easier. So I have this going on here. So if I take a look at this, if I graph by intercepts, that's probably the easiest method to graph these things. So 8x plus 2y equals 16. That means my x-intercept is 2, and my y-intercept is 8. X plus y equals 5. We'll have x and y intercepts both at 5. And then 2x plus 7y equals 20 has intercepts at x equals 10 and y equals 20/7, which is a little bit less than 3. So it's obviously not going to be perfect or anything, but that's kind of what's going on. The other thing is, if I take a look at these equations, every single equation that I have is a greater than or equal to equation. So the variables must be greater than the numbers. And logically speaking, that means that my shaded region is actually going to be this giant region over here. And I'm trying to minimize things. So since I'm trying to minimize things, these are the only 2 points that I can actually look at. Um, this line that I'm tracing over in red is a little shaky in terms of where that intersection point actually is, because I had a questionable y-intercept in terms of like how I was graphing it, but it looks like it's at 3, 2. So I'm going to confirm that 2 times 3 plus 7 times 2. If it equals 20, then I know that it works out. That's 6 plus 14, so that is 20. So that means I do have the 0.32 that I'm looking at and the 0.14. So if I check those 2 points, I can figure out which one will actually minimize our cost. And it appears that it is 3, 2. So the minimum cost is 3 pill 1s and 2 pill 2s, and that cost is $1.05 per day for Ilmark.